On a CD, there are concentric grooves which run along the back, which help it store information that we decide to put on it. They also lead to the interesting property of these strange diffraction patterns, like colorful patterns occurring on the shiny side. And today, I just want to do a simple experiment just for my own interest to find the spacing between these grooves using a diffraction pattern setup. So let's get to it. This is the experimental setup we're going to be using today. This is a laser supported by some books. Any laser will do. This laser has a wavelength of 650 nanometers. Make sure you get one with a known wavelength. And this is a CD. I removed the sticker from it so that some of the plastic layer is exposed. That's what has the grooves on it. And just a safety warning that I'm just going to put up right now about lasers. So the plan is that the laser will shine onto the wall and it will create a diffraction pattern. Okay, so the first step that we need to do is measure the distance between the CD and the wall. So I'm just going to be doing that right now because it's going to be quite important to use in our calculations later. It's got the assistance of my mom. So make sure you line it up nice and neat. Try and bring it in a straight line towards the wall. 114.2 centimeters. Turning off the lights. Take a moment to appreciate the beauty. And let's start work. So while I'm working, I'm going to be standing with my back facing the laser and basically not entering the level that the laser is at. So I'm going to be using masking tape to mark down the places where the orders are. So this is the order 0 maxima, order 0 bright spot basically, and that is those two are order 1 maximas as well. So this is basically where the light superposes and basically light waves add up, forming a bright spot. I can mark down the positions with a pencil and I can measure the distances later in safety. Now I've turned the laser off and I'm going to make my measurements. So first I'm going to measure the distance between this order 1 and the central bright spot. So that's 55 centimeters. 55.5 centimeters. So now, this is owing to inaccuracies in my scribbling down of the orders. I'm going to calculate the mean and I'm going to use that to do my calculations. 55 plus 55.5 divided by 2 is 55.25 centimeters. Now for the calculation part. So this is the distance to the wall. Let's just call it y. This is the distance from order 0 to order 1. Let's just call it x. And this is the magic equation we're going to be using today. D sine theta equals n lambda, where d is what we want. D is the spacing between the grooves. N is the order, lambda is the wavelength, which is 6.5 times 10 to the minus 7 meters, and sine theta. How do we get theta? X, Y. This is why we measure those. And we can use trigonometry to get theta. Here's the grating, and this is the angle going from here to here. So we can use trig, as I said. Tan theta equals x over y. So theta must be arctan of this. So we know that order number 1, sine of theta is 0.4355 and lambda, as I said before, is 6.5 times 10 to the minus 7 meters over 0.4355 sine theta, basically. Here we go. Which is 1.4925 times 10 to the minus 6 which is approximately 1.49 times 10 to the minus 6 meters. So that means that the grooves on this CD are spaced 1.49 times 10 to the minus 6 meters apart.